Now that we have gone over the many different types of EAS reactions that can happen, we're going to start to study what happens when we don't necessarily just use benzene, but we use a derivative of benzene. And so the groups that are attached to the benzene already will dictate positions that the incoming groups are substituted at. To start with, we're going to talk about activating groups. And so I've given you a table in the notes to look at that's in your book, and I would highly recommend you look at that table. It tells you the difference of activating groups and deactivating groups, and it talks about whether they're weak, moderate, or strong, and they will be weak, moderate, or strong for both activating and deactivating. You also want to take into consideration that activating groups activate the ring to do these types of EAS reactions, and so they'll speed up these reactions, while deactivating groups do the opposite. Since they're trying to deactivate the ring, these reactions will slow down. So to begin with, we are going to look at whether this reaction here, we have phenol, the OH group attached to the benzene ring is an activating group, and we're trying to do a nitration, and that's why you see HNO3, H2SO4. And you can see on the right, I'm asking, is it going to be ortho, para, or meta that is favored in this reaction? To figure this out, you have to draw resonance structures for all possible products. And so that's what I've done or started to do below. We have the ortho, we have meta, and we have para sigma complexes. And we're going to draw resonance structures to figure out which ones are more stable, so we could figure out what products will be formed in the majority. So that's what I'm going to do right now. We're going to draw the resonance structures, starting with ortho. So there's our first resonance structure. There's another resonance structure. And right here, you may tell yourself that can't go any further. I've done the resonance in the ring. What you have to pay attention to is what that substituent that was already on the ring can do. And so since this is an activating group with lone pairs, we can go ahead and dump electron density towards the ring and have another resonance structure. So the positive charge moves up into that oxygen. We're still in this sigma complex. So at the ortho position, what looks like right now is I can draw 4 resonance structures. But this problem's not done. Now I need to assess meta and para. So again, need to draw resonance structures, and that's what I'm going to do now with meta. Okay, and what we're going to see right here is that I'm only able to draw 3 resonance structures. All right, the positive charge misses the carbon where the alcohol is attached, or our phenol, and so the oxygen can't help support the positive charge in this sigma complex. Now lastly, we have to do this for para. And again, what you'll notice for para is that the oxygen is able to play a role in the helping out of balancing or stabilizing that positive charge. And we get a fourth resonance structure. So what we can see here is that ortho has 4 resonance structures, meta has 3, and para has 4. Now again, if we think back to the first video I made, I mentioned that these sigma complexes, they have high activation energies because we go from having an aromatic ring to a non-aromatic ring. And when that happens, you need to have energy to overcome this activation energy, and you have to get over the hump of the intermediate. So what we're trying to figure out here is which one will be the fastest, which one has the most stable intermediate, so that that hump or that activation energy is not the highest, and it will go through that pathway the fastest. So what we're looking at here is the ortho and the para will be the most stable, and this is going to be the case for all activating groups, is your ortho and para will be the most stable. Some of them will have a situation like we see here with the phenol, where we can do resonance into that substituent that's already on the ring. While some of them don't do it, but they still will favor ortho and para. And one of those examples would be an alkyl group that I talk about in the notes. So please look at that and make sure you understand that. But again, all activating groups, they'll speed up a reaction, or the EAS reaction, and they favor ortho para. So I'm going to go ahead and block that out. Ortho para is major. The meta is minor. And that will be the case for all activating groups.